China's mountain monster, building Asia's most dangerous tunnel. Imagine standing at the foot of a mountain range that extends across 1,600 kilometers of untamed terrain. Now picture more than 20,000 workers descending into the depths of this geological fortress every single day, operating machines so powerful their mechanical roar echoes through caverns carved from solid rock. This is the story of one of modern engineering's most audacious gambles, a project that Western experts openly doubted could ever be completed. A tunnel so technically demanding that even America's elite construction teams looked at the blueprints and backed away. But China didn't back away. Instead, they doubled down on what many called impossible. What you're about to discover is how a nation transformed an engineering nightmare into a triumph that rewrote the rules of infrastructure development. This is the untold story of the Qinling Tunnel, and why its success matters far beyond China's borders. The Qinling mountain range has stood as nature's great divider for millennia. Stretching like an enormous stone dragon across central China, these peaks don't just separate landscapes, they split entire climatic zones, ecosystems, and human communities. To the north lies the Guangdong Plain, a region of flat, fertile land that has been China's agricultural heartland for thousands of years. To the south, the terrain changes dramatically into the rolling hills and river valleys of the Hanjiang Basin, where subtropical moisture creates a completely different world. For generations, this geographical barrier created more than just scenic beauty. It created isolation. The only way to move between these two regions was a serpentine road that twisted and turned along mountain slopes, clinging precariously to cliff sides. The straight-line distance? A mere 80 kilometers. The actual travel time? Several grueling hours of winding through hairpin turns and steep grades. This wasn't just an inconvenience, it was an economic stranglehold. As China's economy modernized in the late 20th century, the Qinling Range became an increasingly critical bottleneck. Tourism exploded across the region. During peak seasons, more than 300 million visitors would flood into areas on both sides of the mountains. Every single day, tens of thousands of vehicles would squeeze onto that ancient mountain road, creating traffic jams that could stretch for hours. The old highway had been designed to handle perhaps 20,000 vehicles per day. But demand had far exceeded that threshold, and the infrastructure was buckling under pressure. Overloading became routine. Accidents became common. Economic opportunity was being strangled by geography. Something had to change. In the early 2000s, Chinese officials began developing an ambitious solution. Rather than building yet another surface road that would wind through the mountains, they proposed something far more radical. They would go straight through, underground. The plan called for an 18-kilometer tunnel system that would pierce directly through the Qinling Range. It would be a double-bore design, two parallel tunnels, each with two lanes, allowing traffic to flow smoothly in both directions. Vehicles would be able to maintain speeds up to 80 kilometers per hour, and the system would comfortably handle more than 30,000 vehicles daily. The projected cost? $560 million US. The timeline? 6 years from groundbreaking to completion. The standards? First-level safety certification with a design lifespan of 100 years. On paper, it looked impressive. In reality, it looked nearly impossible. There was virtually no precedent in Asia for constructing a highway tunnel through geological conditions this complex. The Qinling Range wasn't just hard rock. It was a chaotic mixture of fault lines, underground water systems, and stone formations that had been twisted and compressed over millions of years of tectonic activity. Chinese officials knew they needed outside expertise. They sent a delegation of engineers to the United States to consult with tunnel construction specialists and learn from American experience. The Americans listened to the proposal. They studied the geological surveys. And then they delivered a sobering assessment. A project of this complexity, they explained, would require at least $1.7 billion in the United States. The construction timeline? At least a decade, possibly longer. These weren't criticisms. They were realistic engineering assessments based on Western construction costs and methodologies. But for China, these numbers represented a complete deal-breaker. Tripling the budget and extending the timeline by 4 years would fundamentally undermine the project's purpose. Yet abandoning the plan wasn't an option either. The economic pressure was too great, and the strategic value too significant. Chinese engineers faced a stark choice: find a way forward that no one else had discovered, or accept defeat before construction even began. They chose to push forward. Construction officially launched in March 2001. 12,000 workers were mobilized to the site, ready to begin what would become one of the most challenging infrastructure projects in modern history. The problems revealed themselves almost immediately. When engineers conducted detailed geological surveys of the mountain interior, they discovered something that made even experienced professionals nervous. The Qinling Range wasn't just difficult terrain. It was essentially every tunnel engineer's worst nightmare compressed into a single location. In standard tunnel construction, engineers are taught to avoid certain geological features at all costs. Active fault zones where the earth is still shifting, areas with high concentrations of groundwater that can flood a worksite, rock formations prone to sudden, violent fracturing. The Qinling Range had all of these problems, simultaneously, throughout the entire planned route. The groundwater situation alone was terrifying. Water levels fluctuated wildly within the mountain, responding to rainfall and underground flows that were difficult to predict. In the worst areas, engineers calculated that a single water inrush event could release thousands of cubic meters of water per hour, enough volume to completely flood a construction zone in just minutes, sweeping away workers and equipment alike. But water wasn't the only threat. The Qinling Range sits at the geological boundary between North China and South China, two massive tectonic blocks that have been pressing against each other for millions of years. This creates what geologists call extreme ground stress. In practical terms, it means the rock deep inside the mountain is under enormous compression, 3 to 4 times higher than what engineers would consider normal. This compression creates a phenomenon called rock burst. Without warning, the stressed rock can explosively fracture, launching fragments at high velocity like natural shrapnel. These aren't small pebbles. Individual pieces can weigh several tons. A rock burst can destroy machinery, injure or kill workers, and block tunnels with debris that takes days to clear. During the excavation process, construction teams documented 721 separate rock burst events. That's more than 3 out of every 4 meters of tunnel experiencing this violent geological phenomenon. And if that wasn't enough, the rock itself presented its own challenge. Much of the mountain was composed of granite, one of the hardest natural materials on Earth. Laboratory testing showed some sections reached a compressive strength of 316 megapascals. To put that in perspective, that's considered ceiling-level hardness in the geological engineering field. 96% of this granite was composed of quartz, a mineral notorious for its ability to destroy cutting tools. Traditional tunnel excavation equipment simply couldn't handle it. Cutting efficiency dropped by more than half, and tools that normally lasted for kilometers would be completely worn out after just 100 meters of progress. Every single tool blade cost around $5,000. In harder sections, that price could spike to $8,000 per blade, and they were being destroyed by the hundreds. Western engineering firms looked at this combination of challenges and saw an impossible equation. The technical problems were solvable individually, but combined together in a single project with a tight budget and aggressive timeline, many believed China was attempting the impossible. When engineers become innovators, faced with obstacles that seemed honestly insurmountable, Chinese engineers did something that would define the entire project. They refused to accept that existing solutions were the only solutions. Rather than relying solely on their own expertise, they launched a nationwide collaboration. Top specialists in tunnel construction, geology, civil engineering, and materials science were brought together from across the country. International consultants were invited to contribute their knowledge. The project became a massive brainstorming exercise that lasted for months. Slowly, innovations began to emerge. For the groundwater problem, Chinese engineers developed a sophisticated prediction system using numerical simulation and artificial neural networks, advanced computational methods that could analyze geological data and forecast where and when water inrush events were most likely to occur. This allowed them to prepare protective measures in advance rather than simply reacting to disasters as they happened. The rock burst challenge required even more creative thinking. Engineers working in high-risk zones began wearing military-grade protective equipment, bulletproof vests and helmets designed to protect against high-velocity fragments. In areas where geological surveys indicated extreme rock burst risk, they constructed bridge-shaped steel frame structures to reinforce tunnel walls before excavation even began, creating a protective cage that could contain explosions of rock. Temporary protective nets were installed throughout work zones. These weren't simple fabric barriers. They were complex weaves of nylon and steel wire designed to catch multi-ton fragments traveling at dangerous speeds, protecting both workers and expensive equipment. Perhaps most impressively, Chinese materials scientists developed an entirely new anchoring technology specifically for this project. They called it the negative Poisson's ratio anchor rod, a support system that combined high tensile strength with unusual flexibility. When rock began to fail, these anchors could absorb and redistribute stress, effectively buying critical seconds or minutes for workers to evacuate before a major collapse occurred. But the hardest problem, literally, was the granite itself. China's reputation as an infrastructure maniac wasn't built on accepting limitations. If existing tools couldn't handle the Qinling granite, they would invent new ones. Chinese engineers designed a revolutionary tunnel boring machine specifically for ultra-hard rock. Traditional TBMs used a simple roller cutter system, essentially circular blades that would grind away rock through mechanical pressure. This worked adequately in softer stone, but in hard granite, the cutters would dull rapidly, progress would slow to a crawl, and maintenance would consume enormous amounts of time and money. The new Chinese machine used a hybrid approach, dual cutting systems working in coordination. One side featured traditional roller cutters, but these were paired with high-pressure hydraulic water jets that would fracture rock at a microscopic level just before the mechanical cutters made contact. This combination reduced the pressure required for excavation by 30 to 40% and extended the lifespan of cutting tools by 25%. It was a breakthrough that made the impossible suddenly feasible. The air problem no one talks about. As construction progressed and the tunnel began to take shape, engineers confronted a challenge that's easy to overlook, but honestly, absolutely critical: breathable air. An 18-kilometer tunnel is not just a road, it's a potential death trap if ventilation fails. Think about what happens inside a long tunnel. Every vehicle entering produces exhaust containing carbon monoxide, nitrogen oxides, particulate matter, and dozens of other potentially toxic compounds. In an open environment, these gases disperse harmlessly. Inside a confined space, they accumulate rapidly. Without proper ventilation, a long tunnel can transform into a gas chamber within hours. Drivers would experience dizziness, nausea, and eventually lose consciousness, all while traveling at high speed. The potential for catastrophic accidents was enormous, but solving tunnel ventilation for an 18-kilometer passage through a mountain range wasn't as simple as installing a few fans. Chinese engineers spent months running complex computer simulations, building scaled physical models, and conducting wind tunnel experiments. They created digital replicas of the entire tunnel system and simulated countless scenarios: high traffic, low traffic, different vehicle types, different speeds, seasonal temperature changes. The solution they developed was, well, unprecedented in its scale. They designed a system of 3 massive vertical ventilation shafts that would be drilled from the mountain surface down to the tunnel level. The deepest of these shafts would plunge 661 meters, taller than Shanghai Tower, one of the world's highest skyscrapers. Constructing these vertical shafts required an additional 8,000 workers deployed in 2005. The engineering was as challenging as the main tunnel itself, drilling straight down through hundreds of meters of solid rock with precision, ensuring the shaft would intersect with the tunnel exactly where planned. At the surface terminus of each shaft, powerful ventilation equipment was installed. These systems would operate continuously, creating a constant flow of air throughout the entire tunnel network. Contaminated air would be extracted from the tunnel, and fresh air would be pushed in, creating a complete atmospheric circulation system. The result? Even with thousands of vehicles passing through daily, air quality inside the tunnel would remain comparable to outside conditions. Drivers would breathe the same clean air whether they were above the mountain or passing through its heart. The day the mountain was conquered. In January 2007, exactly 6 years after construction began, the Qinling Highway Tunnel officially opened to traffic. The completion itself was a statement. Western estimates had predicted at least a decade for construction. China had delivered in precisely the time frame they had originally proposed, defying not just geological obstacles, but international skepticism. The impact was immediate and transformative. A journey that had previously consumed more than 2 hours, winding through treacherous mountain roads, navigating switchbacks and steep grades, now took less than 30 minutes. Travel efficiency improved by more than 90% virtually overnight. But the significance went far beyond travel time. The tunnel fundamentally changed the economic geography of the region. Cities that had been isolated by the mountain barrier suddenly had direct access to each other. Goods could move faster and cheaper. Tourism became more accessible. Labor markets that had been separate could now integrate. Investment that had been deterred by logistical challenges began flowing to previously remote areas. The Qinling Tunnel was more than infrastructure. It was economic transformation carved through stone. International engineering communities took notice. What China had accomplished in 6 years, under budget, through geological conditions that had seemed prohibitive, forced a reassessment of Chinese technical capabilities. This wasn't just competent construction. This was innovation under pressure, problem-solving at the highest level. Many engineering publications began referring to it as Asia's #1 tunnel, a recognition not just of its scale, but of the technical sophistication required to complete it. But China's ambitions didn't stop with mountains. In 2009, just 2 years after completing the Qinling Tunnel, Chinese engineers launched an even more audacious project, the Hong Kong-Zhuhai-Macau Bridge Undersea Tunnel. If tunneling through a mountain had been difficult, tunneling under the ocean added entirely new dimensions of complexity. The undersea tunnel spans 5.664 kilometers, making it one of the longest immersed tube tunnels in the world. Rather than drilling through bedrock, this tunnel was constructed using massive prefabricated sections called immersed tubes. 33 of these gigantic concrete and steel structures, each larger than an aircraft carrier, were manufactured on land, floated into position, and then carefully lowered to the seafloor more than 40 meters below the surface. The final tube segment alone required steel equivalent to 60 Eiffel Towers. The engineering specifications were staggering. The tunnel was designed to survive for 120 years with minimal maintenance. It had to withstand magnitude 9 earthquakes. It needed to resist Category 16 typhoons, the most violent storms the region experiences. And it had to be strong enough that even a direct collision from a 300,000-ton vessel wouldn't compromise structural integrity. These weren't theoretical scenarios. They were real dangers in one of the world's busiest shipping lanes. The successful completion of this project demonstrated that China's expertise had evolved beyond traditional civil engineering into genuinely cutting-edge construction technology. They weren't just catching up to Western standards. In specific domains, they were setting new benchmarks. Over the past 15 years, China's infrastructure development has accelerated at a pace unprecedented in modern history. The country now operates the world's largest high-speed rail network, spanning more than 40,000 kilometers. It has constructed more than half of the world's tallest bridges. Its port infrastructure handles cargo volumes that dwarf any other nation. But perhaps more significantly, China has begun exporting this expertise. Across Africa, Chinese construction companies are building railways, highways, and port facilities. In Europe, Chinese firms have won contracts for major infrastructure projects. In Asia, Chinese engineering is reshaping regional connectivity through initiatives like the Belt and Road Program. This represents a fundamental shift in global construction dynamics. For decades, massive infrastructure projects were primarily built by Western firms. European and American companies dominated international bidding for bridges, tunnels, dams, and transportation networks. That era is ending. Chinese construction companies now regularly compete for and win international contracts, often delivering projects faster and at lower cost than traditional Western competitors. Whether this represents superior efficiency, lower labor costs, strategic subsidies, or some combination remains debated. But the market outcomes are undeniable. Critics point to concerns about labor practices, environmental standards, and the political strings sometimes attached to Chinese infrastructure investments. These are legitimate questions that deserve serious scrutiny. But what cannot be disputed is the technical capability itself. The Qinling Tunnel wasn't an accident or a fluke. It was the product of systematic investment in engineering education, aggressive technology development, and a willingness to attempt projects that others considered too risky. It represented a philosophy that engineering limitations are problems to be solved, not barriers to be accepted. Stand today at either entrance to the Qinling Tunnel and watch the endless stream of vehicles disappearing into the mountain. What you're witnessing is more than traffic. It's the physical manifestation of human determination overcoming natural obstacles. Every vehicle that passes through in 30 minutes instead of 2 hours represents time saved, fuel conserved, economic opportunity enabled. Multiply that by thousands of vehicles per day, hundreds of days per year, and what emerges is an entirely transformed regional economy. But the deeper lesson isn't about one tunnel or even one nation. It's about how quickly the impossible becomes routine when engineering ambition meets genuine need. The challenges that faced Chinese engineers in 2001, unpredictable groundwater, violent rock bursts, granite harder than cutting tools could handle, weren't abstract problems. They were life-threatening dangers that killed workers and destroyed equipment. Yet engineers found solutions. They developed new materials, invented new machines, and pioneered new methodologies. What had never been done before became not just possible, but repeatable. This is how infrastructure frontiers advance. Not through incremental improvement of existing techniques, but through necessity forcing innovation. The Qinling Range demanded answers that didn't exist, so engineers created them. And those innovations don't stay confined to a single project. The tunnel boring machines developed for Qinling granite have since been used in other hard rock tunneling projects. The ventilation systems designed for extreme-length tunnels have informed designs elsewhere. The rock burst protection methods have been adapted for mining and other applications. One ambitious project in central China has rippled outward, contributing to engineering knowledge globally. China's infrastructure story is far from finished. The nation continues to face enormous geographical challenges, from the Tibetan Plateau to the South China Sea, from western deserts to eastern megacities. Each obstacle demands new engineering solutions, and each solution adds to the growing body of expertise. The question for other nations isn't whether China can build impressive infrastructure. That debate is settled. The question is whether and how other countries will respond. Will this spark a global renaissance in infrastructure investment, with nations competing to upgrade their own transportation networks, energy systems, and urban frameworks? Or will economic constraints, political disagreements, and regulatory barriers prevent ambitious projects from moving forward? The answer will shape the 21st century as profoundly as railroads and highways shaped the 19th and 20th centuries. Because infrastructure isn't just about bridges and tunnels, it's about determining which regions thrive economically, which populations have access to opportunity, and which nations can effectively connect their people and resources. The Chinling Tunnel is ultimately a story about refusing to accept limitations, about looking at a mountain that had divided communities for thousands of years and deciding that division was no longer acceptable, about taking what experts called impossible and making it routine. 20,000 workers descended into darkness day after day,